Hello, in this video we're looking at area between curves. So just to get started, remind ourselves of a motivation for the definite integral way back when we started talking about this idea. And that was area, finding the area under the curve, specifically the area under a function that's positive over an interval. So by under the curve, we mean between the curve and the x-axis, something like that. So what we're looking at now is a slight modification of this problem, that we're no longer restricting to the area of the region below the curve, something like this, which we meant and above the x-axis, but rather between two curves. So something maybe like this guy right here. So now I'm bounded above by this, looks maybe possibly parabolic, and this that looks maybe trigonometric, maybe sinusoidal or something, sine, cosine, something like that. So this would have been kind of the old case. This would be the new thing now. And what I've got here at the note at the bottom, if we think of the x-axis as the lower curve defined by certainly reasonable function f of x equals 0, or so like just y equals 0, then our previous case is actually falls under the same guideline. So if I had this function here, whose graph is the x-axis, it would be bounded by, the region would be bounded by two curves. Right? So what we've done before is actually a specific case of this more general description, more general principle. So when we first started doing this way back when, we found the area by starting with an approximation. And so let me jump ahead to this graph. So the idea was we split this up into a bunch of subintervals of equal width. I'm not worried about how accurate that is, except that's pretty bad. Something like that. And then we approximated using rectangles, right? That was the idea. And there were reasons behind doing that. One, we know the area of a rectangle very well, and so we can come up with this approximation with fairly minimal effort in terms of computations, nothing too crazy, and it also generalizes very nicely. Oops, I'm talking about here. But the idea was as n increases, so n, that's the number of rectangles. The number of subintervals. Each subinterval length is the dimension of one side of the rectangle. But as n increases, these approximating rectangles, if we have a continuous function f, fill the space better and better, and that limit yields a definite integral, which is the exact area. So that's how we built up to it. So got maybe a pretty good approximation here. But if I had, yellow's not great. Let me try a different color, about light blue. It's probably not great either. But you get the idea. When I've got more and more kind of skinnier rectangles constructed in the way that we've talked about. Just went too far. We end up with a better and better approximation. That limit gives us the exact value. That limit is the definite interval. So for the area between two curves, we're going to use the same approach. We're going to start with an approximation and break up our interval into subintervals. So I've got maybe something like that. Only now the height, if you like, the height is the difference of the upper and the lower function values that we use. So let me choose right here. And have a rectangle there, then maybe a rectangle right here, rectangle here. So the construction is the same idea. but my sample point determines not only the full height, but the lower bound height as well. So it's kind of clumsy use of height there, but the difference between the two is the height of the approximating rectangle. And so it looks like that. But again, the setup, it's exactly the same idea. So the sum of these terms, which will give you, it's a Riemann sum, gives us an approximation, and limit produces a definite integral that gives the exact area, just like before. So if I had this many, if I cut the subinterval width in half, I get a better approximation. You know, this is assuming we've got a continuity for these functions. And a little bit more formally, here's what we have. So the area of the region bounded by the curves f and g and the lines x equals a and x equals b, where f and g are continuous, and f is greater than or equal to g for all x and a, b, is given by this definite integral. So there's a lot to unpack there. This is key. So this makes the integrand non-negative. So this is equivalent to f of x minus g of x is greater than or equal to 0. So we're integrating a non-negative function. If we like, we can take our region and think of it as the difference of two functions, that new function on its own, graph that, and then we would have a region bounded above by this curve, bounded below by the x-axis, and it would be what we had talked about before. If that's confusing, don't worry about it. Don't have to think about it too hard. But this is what we've got. So a couple things to keep in mind as you work on this, you're thinking about this. It may be easier to integrate with respect to y rather than x. And we'll see some examples, but you could have something where maybe you've got a curve that looks like something like that. Actually, integrating with respect to x is pretty easy there, but you might find that somehow, so off the top of my head, I didn't do a great job, but we'll see some examples where it's going to turn out that thinking of the rectangles this way is a little bit better. So you have your delta y, and your subintervals going along the y-axis. So just keep that in mind. Next point, if you've got f of x greater than g of x are part of the interval, and then switching the order for the other parts, you have to break up the integral accordingly. So now, imagine you've got something like this, and we want to see the region, the two regions, the total area bounded by those curves. So you got this part, and then you've got this part. But here, f of x is greater, and in the second part, g of x is greater. So what you need to do is find that breaking point, and so then you would have the area above is a to c of f of x minus g of x, because f is the bigger function, plus c to b g of x minus f of x, because over that interval g is the bigger function. If you don't take care of that, if you're not careful, when you integrate from a to b, this is going to be negative in here, and this would be positive. And so if you just integrate from a to b, you would get the net change, or the net area. And that's not what we want. So you got to be careful with that. That's what that note's about. And finally, the bounds a and b might not be given in the problem. So you might have something like this, something real basic, and they say a to b, and so you know that it's this region right here because A and B are given. But instead, you could have, and you will have some examples where it might be something like this, not too different, but you're not told what A and B are. So you got to figure out, what is that intersection point? What is that intersection point? That's going to tell you what A and B are. And then you integrate. So it could be given. It might be that you have to find it. If it's not given, then you find it by just seeing where do these equal, where these graphs intersect, where the functions equal. All right, so a couple things to keep in mind. These problems are kind of easy paced, nothing too crazy, so give you a chance to look at some of the examples, and we'll leave it at that for this video.